Okay, hello everyone. Welcome to the 40th meeting of Introductions in Group Theory Triangulated Categories. Today our speaker is Jordan Williamson from Charles University, Prague, and he'll be speaking to us about duality and definability in triangulated categories.
Great. So thanks a lot for the invitation, Rudy, and thanks to everyone for being here. So I want to talk about this project, which is joint with Isaac Bird. And so it's, unfortunately, despite the seminar name, there's not going to be much group theory. I am really an equivariant homotopy theorist at heart, so I will try and squeeze in one equivariant example because I feel I must. But other than that, it's going to be a lot of triangulated categories. And so the plan is, I want to talk about the story when you talk about modules over a ring. This is about a paper of Holm and Jorgensen, which was really what motivated us to extend this to the triangulated setting. And then the rest of the talk is going to be about explaining how we went about doing that. And then the final part's going to be about an application of this to definable subcategories of triangulated categories. So yeah, there was sort of quite a lot of background. I wasn't quite sure how much to introduce, so there might be too much background for a lot of people here, for which I'm sorry, but hope you'll bear with me. So if we're working in the category of modules over a ring, so then a short exact sequence from L to M to N of R modules is said to be pure if either of the following equivalent conditions hold. And so the first one is for any finitely presented R module, the induced sequence when I apply maps out of C is still exact. And a second equivalent definition is if I could look at the induced sequence when I take the character dual or the Pontryagin dual, which I'll write with a plus. And so this thing here means maps into Q mod Z. And it's pure if this sequence now is split exact. Okay, and so from this, from the second characterization, you see that purity is some sort of weakening of splitting. And so I just have to sort of hit you with a barrage of terminology now, which I'm going to use. So when I've got a pure exact sequence like this, I say that my map L to M is a pure mono, and I say that L is a pure subobject of M, and then I won't write out the other ones, but I say that M to N is a pure epimorphism, N is a pure quotient of M, and M is a pure extension of L and N. So you just sort of stick pure in front of what you would say for a normal exact sequence. And so then the key definition in this setup, which is due to Holm and Jorgensen, is that a duality pair of R modules AB. So it's a pair where A is a subset, or probably a subclass rather, of R modules, and B of modules over the opposite ring. So A is some collection of left R modules, and B is some collection of right R modules that satisfy two properties. And the first one is, if I've got something's in the first class, if and only if, when I take its character dual, it's in the second class. And the second class is required to be closed under summands and finite direct sums. And then the canonical example of this is, for any ring, I look at the flat R modules, and I look at the injective R op modules, and then this is a duality pair. And just because it will become important later on, it's important to know that if my ring's nice, namely Noetherian, then when I interchange these, it's still a duality pair. So this is, under some assumptions on the ring, this duality pair is actually what's called symmetric. Okay, and then the main theorem that Holm and Jorgensen proved using these is the following. So if I've got a duality pair, then you get some nice closure properties of your first class. So namely, your first class is closed undertaking pure subobjects, pure quotients, and pure extensions. Okay. And combining this with some other results, they get sort of the following consequences. So if your first class is closed under coproducts, then it's actually a covering class. So what does this mean? This means that given any R module, there exists a map from something in A to it with some sort of universal property. So any other map from something in A to M must factor through this one. And so this is the pre-covering property. And then the covering property says that if I'm looking at actually maps where this thing is actually F as well, then my alpha is actually an isomorphism. And this is the covering property. Okay, so before I write the other consequences you get from this, I just sort of want to highlight two sort of motivations for these duality pairs then. So the first one is sort of this, which tells you duality pairs govern pure closure properties. And so in triangulated categories, or more recently in tensor-triangulated categories, we like to, you can't hope to classify things up to equivalence or isomorphism. So you instead try and classify them up to this coarser notion of equivalence, when you can build things from one another using certain operations. And so you might care about these operations that come from purity. And then, in this way, duality pairs helps you classify things closed under these operations. And so this is sort of one motivation to look at them. And And I guess this this first consequence of the theorem gives you the second motivation, which tells you that duality pairs are about allow you to construct approximations. So you can always, you can't quite replace an object. You know, this is not, you know, this map is not an equivalence. So you can't replace your object by one with a certain property, but you can always map into it from things with a certain nice property. Okay. And so then there are two more consequences of this that look a bit like this first one. So let me just quickly write those down. So if your first class is closed under products, then it's pre-enveloping. And so this is just the dual notion to pre-covering. I look at maps out of my object rather than into. And finally, if my first class is closed under coproducts, extensions, and the ring is in there, then these things, then you actually get yourself a perfect cotortion pair. So this means that your first class is covering and the orthogonal is enveloping. And so this orthogonal is the X'd orthogonal. I look at things that receive whose X'd one out of things in A vanish. Okay. And I want to just give you a sketch of the proof of the first part of the statement, so that the A is closed into pure subobjects, pure quotients, and pure extensions, because it sort of highlights that the definition of purity that really works from this point of view is this second one about when the dual sequence splits. And so, you know, a lot of the rest of the talk is going to be about trying to understand what this means in the triangulated setting. So let's just prove it's closed under pure subobjects. The other two are very similar. So if we suppose that L to M is a pure mono, and that M is in my first class, and then we have a pure exact sequence like this. And so by definition, when I apply the character dual, I get this split exact sequence. Well, so because M was in A, by definition of a duality pair, its dual must be in B. Okay, but now because this thing's split exact, the dual of M is a summand of the dual of, sorry, the dual of L is a summand of the dual of M. So L plus is in B because B was closed under summands. And then by definition of a duality pair, that just tells you that L is in A. So we've shown that if I've got a pure subobject of something in A, then it's still in A. Okay, and so now the goal then really is to take this and generalize it to triangulated categories. And then apply it to definable. and apply to definability. Okay, so before I move on to sort of the triangulated part of the story, is there any questions? No, okay. So throughout the talk, T is always going to be a compactly generated triangulated category. Okay, and so, you know, if we're going to sort of understand this story in the triangulated setting, we first need to understand what purity is. And so if you look at this definition in the module case, sort of if you look at the first definition, it's sort of clear what you should do in the triangulated case. You have sort of obvious analogs for all these things. And so the sort of the first step for us is actually going to be finding an analog of part 2. Okay, so if you've got a triangle in your triangulated category, you say it's pure if, also for the modules we looked at, we hommed out of something finitely presented. And so the analog in this case is I map out of something compact. And ask for this to be exact for all compacts. And you notice that this is equivalent to asking that the connecting map, when I look at the map from Z into the suspension of X, this has to be the 0 map. And this has a name. This means that the map Z to the suspension of X is a phantom map. I guess because you should think of it as like, you know, the map Z to the suspension of X itself is not 0, but when I map out of any compact, you know, they don't see this map. They all think it's 0, but it might not actually be 0. So it's in some sense a phantom. Okay, and so this definition gives the analog of the first definition of purity in the module case. But this theorem about duality pairs really needed this other notion about the splitting when you apply the character dual. And so I guess the first goal is to then give an analog of this. And so before we could start to do that, we firstly need an analog of the character dual. In your triangulated category. Okay, and so for this we made this definition of what a duality triple is. And so a duality triple, sorry, T, U, and Q. Okay, so here T and U are compactly generated triangulated categories. And now Q, so there's a bit of an abusive notation going on. So Q is a triangulated functor from T op to U, and also a triangulated functor from U op to T. The reason we've called these, so we have two different functors, but we call them both Q. And the reason for this will become apparent shortly. And these have to satisfy some conditions, and all the conditions are sort of natural when you look at what properties the character dual in the module category has. And so the first one is that whenever I apply this functor, I get an object that's pure injective. So this is for either of my two functors Q. And so what does pure injective mean? I won't write it down, but it's just, you take the definition of an injective module, and wherever you would say monomorphism, you write pure monomorphism. So it's just the analog in the pure setting. Okay. And the next one is for all objects, you get a natural map into the double dual. So you see, this is completely normal for the character dual, and moreover, this natural map is a pure monomorphism. Okay, the third one is again all these conditions. Shouldn't be surprising. Then there's nothing really deep going here. It's just a matter of looking what the character dual does and writing the obvious analog. And so it says this composite is the identity. And so what these maps, so this is taking my natural map I on QX, and then this thing is applying Q to my natural map IX. So IX went from X to Q squared X, but now Q is contravariant. So when I apply it, the map flips. And finally, we have Q sends co-products to products. Okay. And so you have this sort of this setup where you have this nice duality functor that somehow mimics the character dual. And so what are some examples of this setting? So the first one is, suppose I've got T, which is now, it's not just a triangulated category, it's a rigidly compactly generated TT category. So this means that it's got a compatible tensor product, it's compactly generated, and the rigids and compacts coincide. If you don't know what it means, it really doesn't really matter. Then I get a duality triple by taking T both times and this functor I, which I'll define in a moment. And so this functor I is the so-called Brown Combinates dual. It takes its name from stable homotopy theory. And how's it constructed? Well, by Brown representability. There's an object I in T with the property that when I map into I, it's just the same as doing the character dual on maps out of the unit. So this looks like a lot of information, but you should just think this is just H0. So the zeroth homology or the zeroth homotopy, and I'm just taking the character dual of that, and then by Brown representability, I can lift this to the triangulated category. And then once you've got this object I, you can define your functor, blackboard bold I. to just be mapping into your object I. So F is the internal hom object in your category. Okay, and so this covers a lot of examples you might care about, such as the derived category of a commutative ring, the category of spectra, G spectra, stable module category, and so on. And so the fact this is a duality triple can be extracted from a paper of Christensen and Strickland. Okay, and then, so this is sort of, it's not really a topological example, but a lot of the sort of this point of view is perhaps quite topological. And so for some more algebraic examples, so if I've got any ring R or DGA R, then I can look at the derived category of R, the derived category of R op, and just the usual derived character dual. And this is a duality triple again. And I won't write it down, but you can extend this to any algebraic triangulated category. So anything that looks like the derived category of a DG category. Okay, and then, so now we've got this setup of duality triples. What we wanted is to be able to detect pure triangles using it, as we could in the module case. And so this is precisely what the following theorem says. So if I've got duality triple, then if I've got a map, so the definition of duality triple was completely symmetric. So I'm going to not say either in T or U, and it can be in either. So a map's phantom. If and only if once I've applied this duality functor Q, I get the zero map. Okay, and then from this, you get, therefore, that a triangle X, Y to Z is pure if and only if when I applied this duality functor Q, it's split exact. Okay, and so you see this is sort of just an analog of the result in the module case where Q was the character dual. And I just want to say this really builds on this paper of Christensen and Strickland that I mentioned earlier. And there's also a paper of Angler, Hugel, and Herbeck that does this in the derived category of a ring. Okay, so is there any questions about this before I move on to the next part? Okay. Okay, so now we've got the setup of we've got this functor that mimics the character dual and it detects pure triangles for you. So now it's to extend the Holm-Jorgensen definition of duality pairs to triangulated categories. It's literally a matter of writing down the definition again. And so let me just copy it to save time. Oops. Okay. Well, maybe I won't save that much time. So some of the people in the talk will probably attest to the fact I'm not very good with the iPad. And so I permanently fail to be able to paste the things I've just copied. Okay, and yes, this is one of those moments. So let me just quickly write the definition out again. So if I've got a duality triple, then a duality pair on this duality triple, it's again a pair. So I've got some A in T and some B in U, such that an object's in the first class if and only if the dual of it is in the second class, and B is closed under retracts and finite coproducts. And so this is really, just the complete analog of the Williamson definition for modules. And so, what examples can we get out of this? And so you get sort of the examples from the module case sort of carry over. So I can look at, if I've got a ring R, I can look at complexes of flat dimension less than or equal to n, and complexes of injective dimension less than or equal to n. And then this is a duality pair on the derived category of the dr op and the character dual. And so, and then there are various similar ones that look like this using, so I can use the Gorenstein flat dimension, or you can use width and depth. And so on. So these are all various algebraic examples. And so for maybe a more TT example, so if now T is a rigidly compactly generated TT category, then given any set of compacts in this triangulated category, I get a torsion functor, a localization functor, and a completion functor. And then the torsion and complete ones give you a duality pair. So I don't really want to say what these things mean in too much detail, but this just means that I take the torsion ones are everything I can build from my compact objects using triangles, coproducts, and tensors. And the complete thing, these are things which are given by mapping out of a torsion thing. Yeah. And so the specific, there are various, you can take various T's and K's and get various interesting ones out of these, but just to name a couple, you can get, if I've got a ring and a finitely generated ideal I, then I can look at the derived I torsion complexes and the derived I-complete complexes. And this is a duality pair. And then my token equivariant example is now if I've got a family of subgroups in a compact Lie group, I can look at the F-free G spectra and the F co-free G spectra. And these are, this forms a duality pair. And there are various others. You can do chromatic examples where you look at, where you take your compacts to be a finite type N complex and build various examples from this. And then one more example. If I've got a ring R and an object, and if this is a silting object, then if you look at the silting class associated to this is the left-hand side of a duality pair, where the right-hand side is given by the co-silting class associated to the dual. And this is our duality pair. Okay, and so I hope there's an example there that at least one that everyone sort of knows and feels comfortable with. And so sort of just the point I just want to sort of emphasize, they crop up all over the place. So being a duality pair is not that restrictive of a condition. And in fact, given any collection of objects, you can always generate a duality pair from it. Okay, and so now we've got the definition. You can just sort of prove the analog of Holm-Jorgensen's main result. Just the proof is exactly the same way as I sketched in the module case. And so if you've got a duality pair on a duality triple, then the first class is closed under pure subobjects. Pure quotients and pure extensions. Okay. And so you get all these nice closure properties, and then if you combine these closure properties with a paper of Lake and Victoria, you get the following corollary, where we unfortunately have to assume T is algebraic, which just means it looks like modules over a DG category. Okay. And so then if A is coproduct closed, it's pre-covering. If it's product closed, it's pre-enveloping. And if it's coproduct closed and triangulated, it's a torsion class. So it's the left-hand side in a torsion pair. So these things you should just think of as exactly the analogs of the results in the module case. Okay, So now we've this is you've got these given a duality pair, you get these nice closure properties, and now you want to play with these to apply it to some stuff. So I just want to state a lemma and maybe give a sketch proof of one of the parts of it, just to illustrate once you've got these pure closure properties, you can really get a lot from it with relatively little work. So now if I've got this duality pair and I assume it's moreover symmetric, so meaning I can interchange A and B and I still get a duality pair. Then you get the following four things are equivalent. The first one's closed under coproducts. The first one's closed under products. And then similarly to the second one. And this is all just really formal messing around with this theorem here now. So maybe let me just prove, 1 implies 4 is perhaps the most difficult. Okay. Let me actually do 3 implies 2. They're the same because it's symmetric, but in my notes I did 3 implies 2, and I'll end up in a mess if I try and do what implies 4 on the fly. And so we suppose we've got some collection of things in A, and we want to show that when we take their product, it's still in A. Okay, and so because AB is a duality pair, I know that when I take the dual, each of these things is still in B. Okay, so this is AB is a duality pair. Okay, but now by assumption, B is closed under sums. So the sum of these things is also in B. Okay, but now, because it's symmetric, BA is also a duality pair. So I can apply Q to this again, and I land back in A. Okay, but now one of the parts of the definition of being a duality triple was that Q sent coproducts to products. So now I get the product of the Q squared xi is in A, and so far I've really done nothing. I've just used the definitions. And then now, if you look at the map from xi into the double dual, this is a pure monomorphism by the definition. And it's still a pure monomorphism when I take the product of it. And so now, because this thing's in A and I'm taking a pure subobject of something in A, this thing is now in A by the theorem that said that A was closed under pure subobjects. And so you really get these quite powerful closure conditions, with relatively little work. Okay. So now I want to look at an application of this to definable subcategories. And so just to save me having to constantly say what T is, I'm just going to assume my T's are rigidly compactly generated TT category. You could also assume T's the derived category of a ring, not necessarily commutative ring, and still do everything I'm about to say, but just for concreteness, let me fix this. Okay, so what is a definable subcategory? So if I'm looking at a collection of things in my triangulated category, it's said to be definable if there's a set of maps between compacts. So these are all maps between compact objects, so that my D is the collection of things, so that when I hom out of Fi, this thing's surjective for all I. Okay. And so this is a slightly, personally, I find this a bit of a strange definition and don't really get the motivation. So maybe a motivation for coming from the more topological side, I guess, is that these definable subcategories, well, if I also assume they're triangulated, then there's a bijection between these definable triangulated subcategories and so-called smashing subcategories. So these are the things which are the acyclics for a smashing localization, or equivalently, they're the subcategories, so that when you include them into the whole thing, you have a right adjoint which preserves co-products. Okay, and so these sort of things, these are the subject of the telescope conjecture, effectively, and so these are an interesting thing to look at from the point of view of TT geometry, and so studying definable subcategories tells you about this by this bijection. So that's one motivation from this perspective. Okay, and so in order to apply this to this duality pairs to definability, yes, we want to reformulate it in terms of some closure properties, and so then there's this theorem due to Laking that tells us we can do this. So if you suppose T has a model, so it comes from a nice stable model category, whatever. Then you've got your class, and it's definable if and only if it's product closed under pure subobjects, and closed under pure quotients. Okay, and so immediately from this you see that duality pairs told you about these two closure properties, and so they should apply to tell you something about definability. And okay, so with time in mind, I will skip a bit and just claim that associated to any definable thing D, there's a dual definable category. Written as D superscript D. And so briefly, just in words, this is constructed by, it's a bijection between definable subcategories and Serre subcategories of the functor category. And so you construct a duality on Serre subcategories, and then by this bijection, this passes to definable categories. And so you always get this dual. And so then using duality pairs in conjunction with definability, you get the following result. So if you've got a definable subcategory, then this thing is a duality pair. And moreover, it's actually a symmetric duality pair. Okay, and sort of, so maybe on its own, this part of the theorem isn't that interesting because you probably didn't care about dual definable categories a moment ago. But the point is when you can then use this in conjunction with some of the closure properties. And so you get if you've got a duality pair, and both of the things are definable, then actually it's symmetric. And you can actually precisely characterize both classes in terms of the others. Because, so if you think about the definition of a duality pair, yeah, there was actually some flexibility in what I took my class B to be. But when I'm in this definable situation, it's actually all determined for me. And finally, I'll just write this one. So if we're in the setting where my T has a model, this is just because I want to apply this this proposition here. But other than that, we're not using any sort of enhancement. And then the following are equivalent. And so earlier we had this result, if I got a symmetric duality pair, then closure under co-products and products were all equivalent for both classes. And now in the definable setting, you can extend this and you get that. So either of them is co-product closed. Either of them is product closed. Oops, I've missed a bit. Sorry, the following are equivalent for A and B, a symmetric duality pair. And so this was the content of the proposition I said before. But now we can furthermore say that under either of these assumptions, A is also definable and B is its dual. Or equivalently, B is definable and A is its dual. And I guess I'm sort of running out of time to say anything else. So maybe in words, I'll just say some more things we did with this or we're hoping to do with this. So I guess let me have time to write this one more corollary because I think it's quite nice. So you can, these duality pairs really let you push checking closure properties to another class that might well be nicer. So checking something's triangulated for a definable thing is the same as checking it on its dual. And similarly, checking something is a tensor ideal is the same as checking it on its dual. Okay. And so in addition to this, we looked at how you can cook up new duality pairs from old ones. So can you localize them to give new ones? And it turns out, yes. And duality pairs and localizations always come from ones above. And sort of another interesting direction, maybe not so much in the closure properties direction, but in the direction of the approximation. So we always said duality pairs give you approximations, but you might hope you can get replacements. So can you get things which are weakly equivalent? And so the question is, can you build model structures, using this data of duality pairs on a triangulated category? And and the hope is that you can build model structures whose cofibrant objects or fibrant objects are determined by these classes A and B. And this is sort of related to some work of Gillespie on model structures on chain complexes. And I guess I'll stop there. Thank you.
Thank you, Jordan. Can we all unmute ourselves and give Jordan a round of applause? We're doing the clapping silently. Yeah, I was holding my iPad in one hand. Okay, thank you, Jordan, for the wonderful talk and for adding in so many details. Do we have any questions for Jordan? I had a few questions, but unfortunately, I've already asked Isaac exactly those questions. So, okay.
Can I ask a question?
Yeah, please go ahead.
Yeah, I mean, you define the dirty triple for a pair of triangulated categories, right?
Yeah.
So I'm thinking if we go back to the classical situation, I mean, go back to the category for both category for modules, something like this.
Yeah.
Can we give more information? I mean, or give more examples of the look? If you choose it's like that you choose Q to be the home blank Q such module Z, then you got the classical direct pair, right?
Yeah.
But if maybe I'm not sure, but I'm thinking maybe if we can choose another Q such that
so
we can get some other kinds of direct pairs, right?
Yeah, so I think you can do it with respect to you take an injective code generator, so like you do mapless duality. But I think from what I remember, you always get the same things pretty much up to maybe taking some products in the second class. I can't quite remember. This is much more Isaac's domain than mine. But I think if you've got this duality given by the character dual, and you're asking if you can do another dual, and I think it's if I have a duality pair with respect to this character dual, I think this probably what I'm writing is not quite true, but I hope that some version correctly interpreted is true. Is a duality pair with respect to this, where this B tilde should be some sort of adding some products into B or something like this. I can't quite remember what the story goes like there. There's a paper of Prest and someone else whose name I unfortunately forget that talks about something like this, I think.
Yeah, Mike was supposed to be here today, but well.
Okay,
Thank you. Thank you for the question, and thank you, Jordan, for the answer. Any other questions for Jordan? So this talk has been recorded. If you forget to ask something now, it will be on YouTube. If you have more questions later, you can of course email me. I can forward them to Jordan, or you can email Jordan directly.
Hi, can you hear me?
Yeah.
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 Hi. I would like to ask, I mean, I don't know if this makes any sense. I mean, did you think about a notion of duality pairs in X-triangulated categories? These X-triangulated categories, the notion in the sense of Nakaoka, Palu, and then.
Yes, I really don't know anything about these, so I'm afraid I can't really say anything now. But I don't think it's something we thought about. So yeah, it's certainly something that we ought to have a look at. So yeah, thanks for that.
Okay, thank you.
Thank you, Sergio. Any other questions for Jordan? Well, in that case, let us thank the speaker again. Keep it. I'm usually a fan of clapping like the old school way, but I'm holding my iPad in my hands. Okay, thank you all for coming. The recording of this talk will be uploaded to the YouTube channel, and I will email everyone the details of the next talk. Thank you. Bye-bye.